This is part 3 in a series of videos in which I'm attempting to start a project in which I want to reverse engineer the firmware and the hardware for this Wren computer system. I have a number of these to repair, but these videos are not really about repairing these units. This is more about generating some meaningful technical documents that other people can use and that I can use to repair Wren computers. Seems there are quite a few of these about, and most of them don't seem to work. The technical documentation seems to be very sparse for these, and so it would be nice if we had something to make these easier to repair. Equipment like this is fairly easy to repair if you have the schematics and the listings for the source code, but when you're flying blind like this, it can be extremely difficult to track down even fairly minor faults. So that's the idea of these videos. I want to try and get other people involved. I've been contacted so far by a few people that want to get involved in the project. The more they get involved, the better. And it will also be a very interesting project. If you're interested in vintage computers, then this is the sort of thing that hopefully you'll find extremely interesting. It's not just about ending up with a set of documents for this. I think the process itself will also be quite fascinating. And that's especially true with this machine because it is quite an unusual design, so I think that will become more apparent as we progress through this project. So far I've put out a request that anyone interested can contact me and hopefully get involved in helping to reverse engineer this system. And so one of the first things I want to do is start work on reverse engineering the firmware. So I've given some very brief overviews and demonstrations of how I go about doing that in the previous video. But of course, if other people are getting involved, then we need to do this in a bit more of a meaningful way, otherwise it would just become extremely difficult and the progress would be too slow. So the first thing to do is I'll make the disassembled source code for the two ROMs available. So I'm most likely going to set up a page on my website to keep the most recent versions of these files available, and as information is fed back to me, and as I work on these, then I'll update the files and hopefully keep them as current as I can. But in order for anyone to be able to really make progress in doing this, then because most people probably won't have access to a Wren, then the easiest way to deal with source code is to try and get some idea as to what the various parts do and how they're mapped within the system. So for example, if we look at a page on the in the source code listing, we'll get things like this. It'll say out as 01D, and well, what does that mean? What's it trying to address? You could blindly go through all this and say, well, it's addressing this device and then it's doing this, this and this. But if you know what the device is, then it kind of gives you a bit of a heads up as to exactly what you're likely to be looking at here. And so that's what I'll be doing, as well as making these documents available, and I'll try to compile and combine all the information as it comes in. I'll also be creating and maintaining a third file, which I'll also make available on the website as well, and that's the map for all the devices on the board. As you can see, it's fairly incomplete at the moment. This is just information taken from the user manual, but it is quite useful. Gives the mapping for the RAM and the ROM. Where it says here in the middle column ROM bank 8 and ROM bank 4, if we look at the start of the code out of each of the two ROMs, if you recall, then it was switching to address 8 hex and address 4 hex at the beginning of the two ROMs, and I'm assuming that's what these two refer to. So bank 4 and bank 8 are obviously the hex addresses for accessing these two ROM banks. They're actually physically mapped to address 0, but this is how they're accessed within the system. So I'll just grab the source code. So this is the first page out of each of the two ROMs, and as you can see, what we have here is it's switching to address 8, which I'm assuming means it's the ROM for bank 8, and the other one for address 4. And again, that gives us quite a good heads up as to exactly what we're looking for in terms of the memory mapping. And also the manual states that the SRAM is mapped to bank 0. And again, that's quite useful because it probably means that if we look through the source code and we see it's writing to address 0, then we can be fairly certain that it's selecting bank 0. But we need to, of course, flesh all this out and make sure that we can fully understand what's going on here. So what I'll be doing is going through and figuring out what all the devices are mapped to, and some devices, such as the floppy drive controller for example, have multiple registers, so there are 4 registers within that device, and of course there is the data bus itself, but that's kind of a different thing. The system needs to be able to select the particular register, and that's the way we go about determining how these are mapped. So in this video I'm just going to quickly go through how I'm going to go about this. And so we'll start with the floppy drive controller. We need to figure out what to put in this end column so that when you're going through the source code you can make sense of any out instructions, and if they are a hit on the floppy drive controller, then you'll know that the bit of code you're looking at is talking to the floppy drive controller. And then looking at the floppy drive controller spec sheet, you'll be able to figure out exactly what command it's sending, or if it's trying to read data, or whatever else it's trying to do. So we'll tend to put some context into the source code that you're trying to unravel. If you don't do that, it becomes extremely difficult, and once you've got some context going, then the process tends to accelerate, because as this all fills in with comments, then of course it all starts to make far more sense. Okay, so the first thing we've got to do is determine how to go about figuring out how the device is mapped. So if we have a quick look at the spec sheet for this, then I won't go through the whole thing. I've been through this in a previous video, but the important pins here are A0 and A1, and they give us access to 4 internal registers within the device. So I'll just get that page of the spec sheet and we'll have a look so we know what the 4 registers actually are. So looking at the relevant page in the spec sheet, we can see here that this section is referring to the A0 and A1 lines, and you can see that when they're both low it's looking at the status register, and it can either read from or write to the particular register. So in read mode it's status, and in write mode it's the command register. And then when we have a combination of 0, 1, it's the track register to set the track number or to read the track number. And when we have a combination of 1, 0, it's the sector register, and when they're both 1, 1, it's the data register. So now we know this, and we know we have the chip select line, then what we can do is use the logic analyzer to capture these events. And if we need to, we can be fairly specific with the logic analyzer to capture the data we're looking for, because it's in general these are consecutively numbered registers, so this is why these lines are referred to as A0 and A1, because they're normally mapped to consecutive memory addresses in the system. So it could be these lines are connected directly to the address bus, in which case they'll be toggling continually, or they could be latched, and if they're latched then the logic analyzer can be fooled by this combination not being valid depending on where you're looking at it. So we always need to look at it directly on the device we're interested in and not on the actual address bus. What we can however do is, when we do capture data, is we can compare the values of the A0 and A1 lines on the device with the A0 and A1 lines on the Z80 itself, and see if there's a direct correlation, so we'll know then if it's a real-time mapping or if there's a latch between the two. Okay, so I'll get the logic analyzer fired up. I'm already connected to A0 and A1 and chip select, so we'll start off with just those 3, and hopefully we'll be able to capture some data and see what address they're actually mapped to. Okay, so on the analyzer I've got this configured. I've got just the chip select and the A0 and A1 lines active in the trigger. I've got A0 and A1 looking for 00, so that is we're looking for any hits on the status register, and chip select as 0, so in other words when the device is selected and both A0 and A1 are low, then in theory the system should be accessing the status or command register. If we want to, we can use the write and read enable lines to determine which of the two we're interested in if we want to look at specific sections of code. In this case I'm just trying to find the address this is mapped to in the system, so we don't need to use that extra line. Okay, so we're hooked up. Go to waveform, arm the analyzer. Just need to set it for a single event. It's currently set to 300. Back to waveform, and so the first time we get a hit on the device we should trigger the analyzer. So I'll press reset on the Wren. Now of course this does rely on the code going through and actually trying to access this particular register, but as we're looking here at resetting the machine and it should be trying to boot from the floppy drive, then in theory it should be accessing all 4 registers within that device. So I'll go ahead and press the reset, and as we can see we have indeed got a hit on the analyzer. So looking at the point where we've been triggered, it's on chip select, and the read write line and in-out request and TIN, which is on the data request line, we can use if we want to figure out what's going on within the code. What we're interested in here is the number at the top. So it's saying 0828, and this is the in-out port address for that particular register. So at the moment we're seeing a value of, and if you're not familiar with the in-out instructions on the Z80, then on the address bus, which is this blue bus at the top, then for an in-out instruction what we're looking for is the top 2 digits are the data value that's being presented to the port, and the bottom number is the port address. So we'll just scroll back a little bit, and that will give us the address that this event occurred in within the firmware. And I'll just grab the page for this, and then we'll see if we're actually seeing an in or an out event in the firmware. Okay, so looking at that address, so AB is the instruction on this line, and as you can see it is indeed an in instruction, and we can see this if we look at the control lines. So down here you can see that we've got the read line is low, so it's reading. In other words, the Z80 has requested data from the controller chip, and that would make sense because as you can see it's an in instruction, and you can see also that the address is 28 hex, and that's the address that we're seeing for the port number. And then if you want to, you can see what value is actually being read. So it's reading F9 from the controller chip, and what you can do then is go back to the spec sheet for the controller chip and see what that number actually represents and see what the chip is doing. Okay, so we now know that the port address for the status register and the command register on this device is 28 hex, so I can write that into the table. Okay, so I've just scribbled that in there for now, but what I'll do is update this as I get more information. And so what we want to do now is look for hits on the next register. In theory these should be incremental, so we should really be 28, 29, 2A and 2B, but we'll test these and just make sure. So the next thing we want to look at is a combination for A0 and A1 of 01. So go back to trigger, and we'll set this to 01. Back to waveform, I'll reset the Wren, and sure enough we have hit, and as you can see the address is indeed 29. So we know that the address for the track register is 29 hex. We'll do the same thing with the next address within the device. So in this case we want 10. I'll reset the Wren, and this time we should get 2A, and indeed we are getting 2A. As I said, the 2 digits before are the value being written to that register. So in this case what it's saying is that, or read from, depending on whether it's reading or writing, and as you can see that's the sector register, so you'll be able to look to see what the sector register is. We want 1, 1. I'll reset the Wren yet again. And so this time we haven't got a hit, and this is where we're getting a problem. It's not getting as far as trying to read data from the device. It's only ever going through the initialization of the device. This is why I don't think the IC is working. And that's one thing to bear in mind as we go through all this. This board is not working. If we had a working machine to do this on, then it would be far less complicated, but it is what it is. This is what we have to work with. But the technique is still the same, and as you can see, what I'm going to have to do is make repairs as we go through this. But again, because we're not getting a hit on the data register, this is a clear indication as to what the issue is. And so the next step is I'll update the table, the map table. So I'll update this, and I'll make these documents available on the on my website. So if you do want to get involved, you can download the 2 source code files and the map file, and then the idea is when we know what these registers are, so we know this is command or status, so what I'll do is in the source code I'll replace the address with the actual name of the register. So I'll write something like FDC status register. So that means that we'll know exactly what's going on here, that this particular line is reading the status register from the floppy drive controller. And then as this gets done throughout the entire source code files, the whole thing becomes readable, and then decoding the remaining parts becomes easier and easier. So as I progress, I'll update these documents as I have done here, and this is what you'll get on the website. I'll just indicate what each of the registers or devices is that's been addressed, and what the address is that it's mapped to within the system. So whenever you see these addresses within in-out instructions, you'll know exactly what particular part of the system is being accessed. And as I said, once you know that, it puts the source code into context and makes it far easier to deal with. One thing to bear in mind if you are following through on this and looking at the various values we're getting, I said this is a bit of a strange value for the particular register we're looking at. So it's the sector register. If you remember, we didn't get a response from the data, so this is still the results of the sector register test. And so it might seem a bit strange that we're getting a value of FE for the sector number, but of course that's because the WD2791, which is what's fitted to this board, has an inverted data bus. That's one thing to bear in mind if you are taking values off the tests I'm doing here, is just bear in mind these values will be inverted. They're not normally inverted in terms of the data on the floppy disk, and you'll see quite often in the source code that the data values read from the floppy drive, whether it's the data or the status registers are inverted before they're used, so the bits are flipped, and that's why. It's because the floppy drive controller chip has an inverted data bus. So this value is actually 1 as far as the sector number is concerned. It's not FE. So just bear that in mind if you are following through on this and making notes of these numbers. Just invert them if we're looking at the value coming directly out of the device itself. Also, some of these buses go through buffers that invert them, so when they get to the Z80 they're already flipped the right way up, and it's one of the things to bear in mind, another reason why having the schematic would be so useful. So don't worry if you see some weird numbers. It might be there's a fault, it might be because that's the way it's supposed to be, but just try and figure out exactly where it is this data is appearing, then it should be fairly easy to determine if it's a fault or if it's just because the data bus is inverted. Okay, so that's it for this video. Like I said, I'll put these on my website as soon as I can. If you want to get involved, then please go ahead, and if you just want to watch, then that's also fine.